probably everyone in here has heard the term pH before, and you have some sense for what pH is. It measures how acidic or how basic a substance is. There's actually a quantitative formula you can use to calculate pH. And we're going to talk about this a little bit today, give a little preview for it. So a couple things we need to know about this. One is that these brackets are a symbol that don't just mean we're multiplying. They also mean molarity. So this symbol means the same as concentration of H3O plus in solution in molarity, which is moles of H3O plus per liter of solution. Right? That's why we talked about molarity as a unit, because we need to understand what that means. So what this means is the way that this log function works, the more H3O plus I put in, when I take the log of that and then include this negative sign, the lower the pH will be. Right, so when we think about molarity, that's moles of solute per liter of solution. So you all have some idea of what a liter is, right? You've probably all had a liter bottle of water that's like a liter, right? It's not a lot. It's a medium-sized bottle, right? So a mole is Avogadro's number of particles. That's a lot of particles. So if you have one molarity, that's 1 mole of particles dissolved in that liter. Right? So most of the liter is water. But if you put a mole of something else dissolved in that liter of solution, that gives you 1 mole per liter. Right? So let's see what we would get for pH. 1 molarity. If I added an acid to water, so let's just say I add an acid. An acid is a substance that has a hydrogen associated with it, that it's capable of giving away. We're going to talk more about this as well. But when I have an acid, what tells me that a substance is acidic is that it has a hydrogen that's willing to give away. How do I know if it's willing to give away a hydrogen? Well, I test that by putting it in water. So if I dissolve my acid in water, there's the opportunity for water, which is H2O, to use its pair of electrons and grab this hydrogen and start sharing those electrons with that hydrogen. So then these electrons that were shared with the hydrogen will stay with the rest of the molecule. And so that would produce something like this. Now the acid doesn't have that hydrogen anymore. And the water now has an extra hydrogen, and that is the same as H3O plus. Right? So using pH is useful because if I put something in water that acts as an acid and gives away a hydrogen nucleus, not the electron, just the nucleus of the hydrogen to a water, I will produce some H3O plus. The more moles of H3O plus I produce in solution, when I figure out how many moles of that I have per liter of solution and plug it in here, that tells me the pH. The lower the pH, the more acid I have. Right? So looking at 1 molarity, plug this in. What's the log of 1? 0. So if I have 1 molarity, the pH equals 0. That's a pretty low pH. 1 molarity, it's not even that concentrated. What if I started with a much less concentrated solution? So maybe I only add a small amount of acid and I produce 0.0001 molarity. Well, 0.0001 is the same as 1 times 10 to the minus 4th molar. So what if I plug that in up here? Well, when I take the log of a number, taking the log of a number is like taking the power of 10. The log of 10 to the minus 4 is negative 4. The log of 10 to the 7th is 7. So if I have 1 times 10 to some number, and I take the log of that thing, I end up with the power as my answer. So this would be a pH of 4, right? Because the log of 10 to the minus 4th is negative 4. So the negative log of 10 to the minus 4, I have the two negatives multiplied together, so I get a pH of 4. And so calculating pH is pretty straightforward if I know the molarity of the H3O plus. And that may depend on how much acid I put in. It may depend on the degree to which the acid actually reacts with water to produce H3O plus. Sometimes when I put in acid and water, every molecule I put in will react and be converted to H3O plus. So it's easy to calculate how much H3O plus I would get if I know how much acid I'm adding. Those are called strong acids. Weaker acids, though, will not fully react. And when I put a little bit of a weak acid in, like if I have a mole of this, some of it will stay in this form, and when it reaches equilibrium, I'll only have a fraction of a mole of H3O plus, and it will be maybe hard to predict how much. Or maybe I won't know won't be able to predict what the pH is. But if I do have the information to tell me how much H3O plus I can make in moles per liter, I just plug that in here, use the log button on my calculator, switch the sign, and that tells me what the pH should be. Likewise, if I know the pH, I can determine how much H3O plus there is. Let's say the pH is 11.2. How do I figure out how much H3O plus is in solution? I would take this formula and rearrange it. Solving for H3O plus molarity, I get 10 to the negative pH power. So I would take 10 to the negative 11.2 power, and that would give me 6.3 times 10 to the minus 12. That is a very small amount of H3O plus in molarity. 6.3 times 10 to the minus 12 moles is a fraction of a mole. It's still a lot of molecules, right? Because a mole is this Avogadro's number of molecules. But 6.0 or 6.3 times 10 to the minus 12 is a small fraction of a mole. That means compared to the normal amount of H3O plus in water, I don't have very much here when the pH is very high, right? That's a basic solution because I've got a base added that really causes there to be a much less H3O plus and for the pH to go up. What's the pH of neutral pure water? Yeah, pure water has a pH of 7, right? At room temperature. So if a pH is 7, does that mean that I don't have any H3O plus? If the pH is 7, I plug into the formula to calculate how much H3O plus there is. 10 to the negative pH. That's 1 times 10 to the negative 7. The pH is 7. So when I plug that in, my molarity of H3O plus equals 1 times 10 to the negative 7. That means I've got 1 times 10 to the negative 7th moles of H3O plus in every liter of water. Pure water. That means water isn't really pure water. If you've got a sample of pure water, you think every molecule in there is water? You're wrong. The water reacts with water to produce H3O plus. That's called an autoionization reaction. So some of the fastest moving water molecules in solution, the fastest moving ones, will collide with some of the other fastest moving ones, and they will transfer an H plus. The collision is strong enough. This water molecule will use its pair of electrons to grab a hydrogen from the other molecule. And this molecule will keep its electrons to itself. So when that exchange occurs between those two substances being added together, there's no way to prevent that from happening, because in pure water, all the molecules are water, and some of them are moving fast enough for that collision to occur with enough energy to exchange that hydrogen. So this water molecule will become H3O plus as it picks up an extra hydrogen. And the other one will become an OH minus as it loses a hydrogen. So there's always some amount of these in solution. If I produce them in a 1-to-1 ratio, and I produce 1 times 10 to the negative 7th moles per liter of one, I will also produce 1 times 10 to the negative 7th moles per liter of the other. Right, so those are the standard concentrations of H3O plus and OH minus in pure water at room temperature. That's why I have a pH of 7. So if I add any acid to the water that gives even more H plus to the water, it produces even more H3O plus, and the concentration of this goes up and becomes greater than 10 to the negative 7, then my pH, when I plug that into the formula, will be less than 7. If I add a base is something that can use a pair of electrons to grab a hydrogen. So if I add a base to water, the base will start picking the hydrogens off of the H3O plus, and the amount of H3O plus will go down. This concentration will become less. And when I plug a smaller number into the formula, I get a higher pH. Questions about that?